Okay, so we finished talking about two-dimensional rotations. It was a little quick, but the reason is because we want to do three-dimensional rotations. That's the key. That's actually the main topic. But before I do that, we're going to start today on three dimensions. So before I do that, just want to recap, right, what we've been doing. So we've been basically emphasizing the aspects of symmetry in quantum mechanics, right? And what we've done so far is to look at translational symmetry. And we found that whenever there's a translation symmetry, there will be an operator that corresponds to translation. And its generator is what gives us momentum. Right, just to recall what we've been doing. And then with 2D rotations, we found that there is in fact a corresponding operator, and that in fact is generated by one single angular momentum operator. Okay, and so what we're going to discover in 3 dimensions is that what we're going to discover in 3 dimensions is that there's also a rotation operator, but now it's going to be more complicated. This guy is going to be e to the minus I, theta dotted into j, where theta dotted into j has now 3 components, 1 to 3, theta I, j I. And this corresponds to the different orientations where you can choose your rotation axis as well as how much you want to rotate by. And so now there will be ji, where I is 1, 2, 3. And now the angular momentum operators come in 3. And actually not trivial, they no longer commute, in fact. They no longer commute. In fact, we'll discover that when we calculate their commutation relations, they will look like this. JA commuted with JB is I epsilon ABC JC. And we'll figure out what to do with this. So this is what we're going to build our way up to understand. But it will take a bit of time to get that, right? So in fact, to get there, we have to back up a little bit and ask ourselves, what is rotation? Okay, what is rotation? And so what is rotation? It turns out is to do with the preservation of angles and lengths. So this is where we need to start to formalize our definition more precisely. And so what I'd like to do is to consider two vectors, right? Now we're in three-dimensional space. And what we're going to do is we're going to define rotations to be the operator such that the dot product of any two vectors remains the same when we rotate the vectors, right? So you can rotate it any way you want, but rotations, by definition, is going to be the operation that leaves this angle and the length invariant. Okay, so let's write that down. So rotation leave the dot product invariant for arbitrary V and W. So more precisely, let's try to explore what I mean by that. What it means is that if I take V and I replace it with a rotated version of V, okay, so R is a matrix, so this is a 3 by 3 matrix, and I act it on V so that it gets rotated. And likewise, simultaneously, I'm going to take W and act R on W so that it's also rotated by the same operator. Then, if I compare the dot product on both sides, what I will have is V dot W will translate into R acting on V dotted into R acting on W, and this becomes V times, or V transpose if you like. Remember that this itself is V transpose W, right? V dot W can be written as V transpose multiplied into W. And this guy is now V transpose R acting into W. So if this is supposed to go into this, in fact, it's supposed to be equal. So to preserve, the dot product for any pair of V and W, that means that we need V transpose W to, in fact, return to itself. That's what it means to preserve the dot product. I want to get the same answer no matter what my V and W is. That means that what? What that means? That means that V transpose R times W must be equals to V dot W. In other words, basically V dot W, there are different ways to write it, it's the same thing. V dotted into R transpose R W has to be equal to V dot W. So because V and W are arbitrary, what does that mean? It means that basically R transpose R has to be equals to the identity. Otherwise, there's no way that you can get the same thing back for any V and W, right? If it's a special pair of V and W, then you can hope that maybe a more specific form of R transpose R can do the job. But it has to work for any pair of V and W. So therefore, R transpose R, this guy here, better be an identity so that you get back V dot that you get that E dotted into I times W. Right, that's what this is. Has to give you back the same thing for any pair. So that's actually one of the first conditions, right? Remember, we're trying to formalize what we mean by rotations. So that's the first condition. Okay, so I'll box it up. But it turns out that rotations is a little bit more than that. It turns out that, so let me just write it down. It turns out that rotations also involve the determinant of the rotation matrix. And it turns out that we need it to be 1. So let me box that up. So together, these two is the formalization of the definition of rotations. So instead of words, right, the equations are that the rotation matrix is orthogonal, right? So this is the definition, if you remember, of an orthogonality. It's sort of an orthogonality condition, right? That the matrix is orthogonal, and this is called special. Special because special just means in linear algebra jargon, special just means the determinant is 1. So why is that so? So I've shown you why this is the case, but why is that so? So it turns out that for rotations, you expect that there's a bunch of rotation angles that parameterize your rotation matrix, right? And so because of that, you expect that the rotation, you expect that the rotation matrix to depend on the angles continuously. Okay, where these are the rotation angles. Okay, it would be very strange if you rotate by 2 degrees versus if you rotate by 2.1 degrees and somehow the matrices differ, it jumps by a great deal. The components of the matrix jumps by a great deal. It would be very strange, and it shouldn't, right? Because all you're doing is just rotate, and then deciding whether you want to rotate by 2 degrees or 2.1 degrees. So, and in particular, you can choose not to rotate at all, which means that you should recover the identity matrix if you choose not to rotate. So if you tune your angle from 2.1 degrees down to 0, then you should just recover the identity matrix. So this is one point, and then so if you do not rotate at all to recover the identity matrix. So therefore, we should expect that R of theta should be continuously connected to the identity. Right? However you want to rotate, right? There must be some finite amount of rotations that you have performed. But whatever the angle is, just tune it down to 0, and that's the identity matrix. Just, don't rotate. So let me be actually a bit more specific than that, right? So I think somewhere in your undergraduate education, you must have been taught that the most common way to think about rotations is to choose an axis. Okay, so let me be more specific. You choose an axis in space, and you just choose how much you want to rotate about the axis. Okay, so the axis is arbitrary, but you need to find a way to describe its orientation, right? And so one axis would take one axis, let's call it r hat, would take two angles, right? So it would take, say, theta and phi to specify the orientation. Okay, so for example, you can just use polar coordinates, right? You can just use polar coordinates. This is the first axis, second axis, third axis. And the angles that these guys make with the axes can serve as a way to specify the orientation of the axis. And then you have to tell me how much do you want to rotate. Okay, how much you want to rotate will give you a magnitude, which I'm going to call psi. Okay, and that would then determine fully what my rotation is. Take my object, choose an axis, specify that rotation angle. So what you see is that I can always tune this angle to 0. And when I tune this angle to 0, doesn't matter what my orientation is, I have to recover the identity. Okay? And because of that, you know that your, so by the way, my theta vector here, in this case, would be the connection of these angles, right? Theta, phi, and psi. That's what I would mean by my theta angle. But again, I can always connect it back to the identity matrix. Okay? So let's see what that means. So consider now the determinant of the rotation angle, determinant of the r when the rotation angle is exactly 0. And like I said, the orientation can be anything you want, right? So maybe I'll just write it as psi equals to 0, and r hat can be arbitrary. Okay? But this is just the determinant of the identity, which of course is 1. Okay? But determinant of r with an arbitrary sign must be continuous in sign. Meaning if you just turn your sign just slightly, you cannot jump suddenly, right? It's continuous. It's a continuous function of the angles. Why? Because the rotation, if you want to be even more specific, because the components of the matrix you will find is just a bunch of sines and cosines of these angles. So it cannot possibly be discontinuous. In fact, it's differentiable, infinitely differentiable. If you want to sound like a mathematician, right? It will be infinitely differentiable. And so it must be continuous. But let's see what happens to this condition here. Okay. So remember that we're right now trying to discover why is there a need for this condition. But let's in fact refer to this condition as well. Let's figure out. So furthermore, if I take a determinant of R transpose R, well, remember determinant of A times B, what is that? Determinant of what? Do you guys remember? If I take a determinant of the product of two matrices, what does that give me? Just remember? I'm testing you guys because I know it's early in the morning. A times B is what? Determinant of A times the determinant of B. Yeah? And so this guy is now determinant of R transpose times the determinant of R. Okay? But what's the determinant of A transpose? How is that related to the determinant of A? Equal. Very good. So therefore, is just the determinant of R squared, right? So that's the left-hand side of this guy, which means, but the right-hand side is identity, so therefore we discover that from the first condition of orthogonality, right, just from the fact that your dot product is preserved. Remember, this comes from demanding that the dot product of any two vectors is preserved. That demands that the rotation matrix is orthogonal, and this orthogonal, it means that the determinant of R can only be plus or minus 1, right? Because the square is 1, so the determinant itself can only be plus or minus 1. Okay? But let's come back to what we just said. Determinant of R with continuous angles must be continuously connected to the determinant of 1. Because this is continuously connected to identity. So in other words, like, if you just imagine, if you set psi equals to 0, the determinant is 1. I now crank the rotation angle away from 0, so it's no longer identity, but it's continuous. So it must be continuously connected, whatever this number is, must be continuously connected to the determinant 1. But yet, the answer can only be two discrete values. Okay, so but this guy can only be two discrete values. So how can it be continuous and only take two discrete values? That means it can only be stuck in one of the values, right? If it's going to be continuous, it can only be stuck in one of these values. It cannot suddenly jump from +1 to -1 or -1 plus 1. So i.e., maybe I should write equal, right? Maybe I should say, and therefore determinant of R hat can only be 1. It cannot, i.e., it cannot jump to -1. Because jumping would mean it is not continuous, right? It cannot be that you rotate to 2.1 and then you go to 2.2 and then all of a sudden became -1. All of a sudden the determinant became -1. Not possible, okay? Because it's continuous. So this is in fact the defining property of the rotation group. Is an orthogonal matrix, and the determinant is 1. At least for 3 dimensions, this is, it is always true for all dimensions, but this is the argument that we make for 3 dimensions. And this will turn out to exclude, and this is why I mentioned the dimension, in 3 dimensions, this will turn out to exclude what we call parity. Right, so for example, this excludes. So R hat cannot be -1, -1, -1, for example. So what does this thing do? This thing takes the x, y, and z axis and flip them all about the mirror, right? So it goes to negative itself. But in fact, this guy satisfies this because it's just a negative identity. So negative identity transposes itself, and when you multiply it to itself, it just suddenly gives you the identity. But the determinant of that guy is -1 times -1 times -1, which is -1. And so, in fact, it excludes something like that. And that actually tells you that, so this is called parity, where you send all the coordinates to the negative itself, and you discover that that means that parity cannot be equivalent to rotation. At least in 3D. Okay. Turns out this is true in all odd dimensions. But anyway, for quantum mechanics, we're only doing it in 3 dimensions. Okay. And I should say, the orthogonality plus determinant 1 has a name. It's called SO3. Okay, SO3, S for special, determinant 1, O for orthogonality, you have orthogonal matrices, and 3 just because we're doing 3-dimensional rotations. Okay. Any questions for me so far? So it turns out that this is also a group. Let's take a few minutes to prove that SO3 is a group. Okay? And it's important to prove that it's a group because, as you will see, it's getting more non-trivial. It's more, the structure of this group is going to be a little bit more complicated. And so it's actually important to make sure that we lay it out systematically. So, SO3 is a group. Let's prove it. Okay, so the first thing is that it needs to be, so let's write down what is the defining property of SO3. The defining property is that it's orthogonal and determinant 1. Okay. Now, the first thing is that it's the first thing to check that is closure. So what does that mean? It means that if you have one matrix that is rotation, and you have another, then the product of that better be also a rotation matrix. So all you have to do is you now check that these two guys are satisfied. Okay, so in fact, the second guy is easy to check, right? Because if you take the determinant of R3, that's just the determinant of R1 times the determinant of R2, which is 1, because both of them have determinant 1. Now let's check this one. This is a bit more non-trivial. So let's do R3 transpose R3. And this means it's R1 times R2 transpose times R1, R2. Okay? So all I've done is substitute R3 for R1 and R2. Then this becomes AB transpose. Remember, it becomes B transpose A transpose. So you have R2 transpose R1 transpose, R1, R2. Okay? And then now you recognize that this part is in fact 1 because we assume that R1 and R2 are both rotations. Right? So this is 1. And then if this is 1, then R2 transpose R2 is also 1. So therefore the whole thing is just 1. You just have to recognize you get 1, and then after that you get R2 transpose R2. Okay? And therefore closure holds, meaning if you have one rotation matrix multiplied by another rotation matrix, you're guaranteed that the result is also another rotation matrix. The result could be very complicated it may be very complicated to interpret geometrically, but you are guaranteed that it's still a rotation matrix from the definition. Okay? And we don't have to prove associativity because associativity just follows from exactly of matrix multiplication. Good. So we don't have to check that. Right? We know that very well. And then the thing is to identify the identity. Okay? But again, because we're dealing with matrices, identity is just the identity matrix, which is rotation, right? It just means rotation, but the rotation angle is 0. Okay? And the last one is the existence of the inverse. And in fact, in this case, we can right away from the definition recognize that the inverse of any element is simply the transpose, right? By definition, because all of them, all the R's in the group satisfy this definition. But by definition, anything that multiplies R that gives you the identity is the inverse. Right? So R transpose is the inverse, yeah, by definition. Okay, and so I would say that the most non-trivial part of this, but once you understand it, it's not difficult. Okay. So what we have here is we recognize that SO3 is a group, but SO3 is also a set of linear operators, right? They are linear operators acting on three-dimensional vectors. So this is also a representation. Remember, representation just means it's a function of group elements that produces a matrix. But this is in fact a matrix. So the representation is in fact the group itself. And why I'm saying this is because now, if you remember at the very beginning, we said that since these guys are continuously connected to the identity, continuously connected to identity, that means we expect that this guy should be written as the exponential of something. So I'm going to write it as e to the I minus I z, okay, where z is the sum over generators. And we're about to discover what it is. Right. In fact, in my notes, I just first assume that R hat is e to the I omega. Okay. The reason why I pull out I minus I is because remember that it will turn out to be permission, right? So Z will turn out to be permission. Okay. And in fact, it would just be theta dotted into the angular momentum operators. But let's one step at a time. Okay, so let's first figure out what is omega. Okay, so what it will turn out is that if you demand that R is an orthogonal matrix, what you see is that this is e to the omega hat transpose, and then e to the omega hat. Okay, and then you can now expand this. Remember, the exponential itself is defined through a Taylor series. So it's I plus omega transpose plus higher orders in omega squared. This guy is I plus omega plus higher orders in omega. Okay, and then when you multiply them together, I plus omega plus higher orders times this guy plus omega transpose plus higher orders. What you want is that this is identity, right? This is the definition of the group. So what it tells you is that if order by order, you should think of this as a Taylor expansion. Or if you don't like what I'm doing here, you think that it's a little bit, it's not very rigorous, you can introduce a parameter epsilon and introduce a parameter epsilon. So if there's an epsilon here, and the transpose, so epsilon is just some very small number, okay? And epsilon times omega exponentiated, the transpose will not affect the epsilon, right? So that's why you know that it will still be epsilon and epsilon here. Then you can say that this is epsilon, this will be epsilon squared, this is epsilon squared, okay? And now you can group this expansion in powers of epsilon, right? Because it's just a number. So you can now view this as a Taylor series in epsilon. And because it's a Taylor series in epsilon, every order in epsilon must cancel out. Okay, every order in epsilon must cancel out. So in particular, the first order already tells you something about omega. Omega in particular must be anti-symmetric because of this. It tells you that omega plus its transpose must be 0. Otherwise it won't vanish. So therefore, omega transpose must simply be negative of itself, i.e. omega must be anti-symmetric. Okay. Now let's assume that omega is anti-symmetric. So what am I doing here? So let me just pause and orient ourselves. Okay, I'm trying to figure out what is the most general omega that will produce SO3 rotation matrix, right? We discovered that this has to be the most general form because it's continuously connected to the identity. So all that remains is to figure out what exactly is omega, what's the form of omega. So now we use the formula for the defining formula, and we've discovered that a necessary condition that it has to satisfy is that the exponent is antisymmetric. Okay? So suppose instead omega is antisymmetric. So I just give you that. So this is a deduction. But suppose it is true, then you notice that R transpose times R will simply be e to the omega transpose, e to the omega. But e omega transpose, we are now assuming is antisymmetric. So the exponent just simply now becomes e to the minus omega, e to the omega. So remember, usually when you multiply, this I think we've talked about at least once, if you multiply the exponential of operators, in general, this is not equal to e to the x plus y. E to the x times e to the y is in general not equal to e to the x plus y. But in this case, it's just minus omega and omega. So they do commute. So I can now combine them. And of course, this gives me 0 in the exponent. Therefore, it's e to the 0, and therefore I get the identity. So what I can say is that R is e to the omega is SO3 if and only if the exponent is antisymmetric. Okay? So let me emphasize, what I did here was to start from the definition and I deduced that it has to be antisymmetric. But how do I know? Maybe if I go to higher orders, maybe I'll get more constraints, right? I only went to first order. Maybe the second order will give you more constraints, and the third order will give you yet more constraints. So instead of going to higher orders, what I did was to simply plug it in to the rotation matrix itself. And I showed that as long as it's antisymmetric, it will in fact satisfy orthogonality. So I don't need to check, right? I don't need to check second order, third order, and so on. And that's why it's an if and only if, right? Yeah, R is orthogonal if and only if the exponent is antisymmetric. So that means we can now go ahead and construct the most general rotation matrix. Okay, so so what's the most general rotation matrix? So the most general rotation matrix omega. So the most general rotation matrix is determined by constructing the most general omega. And note that, let me just note that the dimension can be arbitrary, actually. So far, so let me just say, in quantum mechanics, we really only care about rotations in 3 dimensions, okay? And I motivated the SO3 by specifically appealing to your knowledge of how to construct a rotation matrix in 3 dimensions, right? That was a motivation, but if you just take the definition to be simply this guy and this guy, then I can just write that as SOD instead of SO3. Okay, but this is an aside. If you don't care about that, it's okay, because in quantum mechanics, at least, we only need a 3-dimensional case. But this statement, the most general omega, is simply a superposition of it's a superposition of the basis antisymmetric matrices. This statement is true in any dimension, which is why I put this in parentheses. Okay? So how do you do that? So for example, in 2D, for example, what's the most general antisymmetric matrix? Well, I can write down a J hat. And the antisymmetric matrix will be, well, it's antisymmetric. So that means that the diagonal components are 0. Why? Because I need it to be antisymmetric. So when I transpose it, it needs to be negative of itself. But if I transpose it, the diagonal component stays fixed. And so if it's negative of itself, it must be 0. Okay? But that means that the off-diagonal terms are 1 and minus 1. And I think we've already noted this is in fact the Levi-Civita symbol. So this equal dot means represented by the Levi-Civita symbol in 2 dimensions. Okay? And then in 3 dimensions, then it gets a little bit more interesting. Okay? So it turns out that the first guy, which I'm going to write it as J hat 1, 2, why do I call it 1, 2? Well, I'm running out of space, so let me erase this a little bit, and then I'll continue over here. So in 3D, J hat 1, 2 is, remember, all the diagonal components are 0, but I want the basis antisymmetric matrices, right? Well, actually, we should back up a little bit. So remember, matrices themselves span a vector space. So this is something that you proved in your homework many weeks ago. And now, we actually have to check, strictly speaking, we have to check that antisymmetric matrices themselves form a vector space, okay? And so you can check, and remember, actually the only thing you need to check is that of closure under addition, under superposition, essentially. So if you add, so let's check, okay, so let's do this. So let's check. Okay, if omega 1 and omega 2 are both antisymmetric, then as long as I superpose them with real numbers, okay, well, why do I know it's real? Because the rotation matrix is real, right? So if A and B are real, then A omega 1 plus B omega 2, well, this guy, when you take the transpose, is just A omega 1 transpose plus B omega 2 transpose, and that's equal to negative of itself, right? Because this guy is antisymmetric, that guy is antisymmetric, so it's just A omega 1 plus B omega 2. Okay, and therefore, we have check closure, meaning the superposition of antisymmetric matrices using real coefficients will produce an antisymmetric matrix. Okay, and so therefore, we check that the space of antisymmetric matrices with real coefficients span a vector space. Okay, so now we can safely ask, what are the bases? So that's the first one. That's the only one in 2D. In 3D, I can now choose the 3 non-zero spots. But that means that I can just choose this to be 1, and this to be 0, and this will be -1, right? Because it's antisymmetric, so it's fixed. Once I fix the upper triangular components, and because there are 3 spots, I will just choose my 3 different bases to be the ones that have 1 in one of the slots and 0 everywhere else. And you see that also the 1, 2 corresponds to basically the location of the 1. Right? So this is the first row and second column. Then I have first row and third column. This will be 0, 0, 0, 0, 1, 0, 0, and then this will be antisymmetric. So this is -1, 0. Okay? And then J hat will be 2, 3. That's the last one, where the 1 will be here. So it will be 0, 0, 0, 0, 0, 1. Okay, and then it will be -1, 0, 0. Okay. And that's the basis. These are the 3 basis antisymmetric. 3 basis anti-symmetric matrices in 3D. Okay, and therefore you can check. Let me just finish up with the last sentence. In 2D, rotations in 2D, in fact, you can check, is e to the I, so, sorry, let me write this as I times j hat, okay? And this is I times j hat, I times j hat, I times j hat, okay? So you can check that the rotation in 2D is actually minus I theta times j hat. Okay? You can check this. And likewise, I can write down the most general rotation matrix in 3D as e to the minus I theta 1, 2 j hat 1, 2 plus theta 1, 3 j hat 1, 3 plus theta 2, 3 j hat 2, 3. Okay? So theta 1, 2, 1, 3, 2, 3 are just real numbers, right? The subscript is just to match up with which generator I'm multiplying it by. But what you can say, as we discover, is that these guys are in fact the rotation angles of what I said earlier. You choose an axis and you choose how much you want to rotate. But that would take a bit of discussion, right? So we'll talk about that next week. Any questions for me? Who has seen this before? I'm curious. Rotation. Probably Wei Hao has seen it too many times, but yeah. Okay. See you guys next week.